All right, welcome back, everybody. Here's the second video for this week's treatment on Newton's laws. We are again going to look at more applications of Newton's laws. Let's start off with a classic, the so-called elevator problem. I talked about this in our last video series a few days ago, but let's revisit it. Imagine being in an elevator standing on a scale, as people do. So if you imagine standing on the scale in an elevator, the question is, will the scale reading change? That is, does your apparent or measured weight actually change when you're riding in an elevator? And the answer is a bit tricky. So let's take a look at what's going on. Inside the elevator, the person, of course, has mass m, and that gives them typically a weight downward of mg. The scale, on the other hand, is pushing up on them with a force that I'm going to call force of scale, or if you prefer, you could call it just F or normal or whatever you want to call it. But F of scale is, I think, it might be a little bit more clarifying. So in our free body diagram, force of scale is up, weight mg is down. And the acceleration, let's just say, is going up. So to add the physics in here, we can say the sum of the forces equals m times a. That is force of the scale minus mg equals ma. So the force of the scale, therefore, is equal to mg plus ma. In other words, if the elevator is accelerating upward, then the force of the scale, the weight reading, is going to be heavier than the regular weight mg. The weight reading is going to be heavier by this additional amount, m times a. So if you're accelerating upward, you're going to read heavier. On the other hand, if you have a zero acceleration or constant velocity, you're just going to read your regular scale. So accelerating upward, you feel heavier than normal. Accelerating downward, you feel lighter than normal. Since the acceleration is negative, look at the expression again. The scale reading will read less than mg. And if the unthinkable were to happen, then the cable were snapped, then the acceleration would be negative g, so the scale reading would be 0, and that is, of course, the meaning of weightlessness. So there you are. Now let's talk for a few minutes about circular motion, which is a big application of Newton's second law. So I want you to recall the first law that says that if an object is in motion, it remains in motion at a constant velocity. But that's not just constant speed, that's also in a straight line. For something to travel in any kind of curved path, whether it's a circle or an ellipse, a curve, or even to take a turn, you have to have an external force. There must be an external force present. So, examples. Well, the Earth orbits the sun thanks to the force provided by gravitation, the gravity between the Earth and the sun. A car can take a turn because there's force provided by friction with the road. Otherwise, if you think about it, the car would continue straight. That's what happens after all if you hit a patch of ice, and it's terrifying, right? Roller coaster cars make a turn, and that force is provided by contact force with the track and the geometry and engineering of the track itself. Let's go really tiny. An electron in a hydrogen atom orbits a proton because the force is provided by the electrostatic force between the electron and proton, the Coulomb force. If you have studied anything in chemistry before, you might know it as a Coulomb force. Now, I'm going to give this to you without derivation. The centripetal acceleration is given by v squared over r. This is an odd little derivation that it makes sense to sort of omit at this point. But the important thing to know here is that this acceleration, which comes from what we call a centripetal or center-directed acceleration, it's not something new. A centripetal force which causes anything to go in some type of curved path or orbit, I should say, or a circular path. It's not a new force, it's always caused by something, but the acceleration can be given by this expression. In other words, wherever we see acceleration for something that's moving in a curved orbit, in a circular path, for example, we're going to look mostly at circular paths. Whenever we see that, we can substitute for the acceleration as v squared over r. Okay, so this so-called centripetal or center-directed acceleration can be represented by v squared over r. Again, this is being given to you without any derivation. Let's look at how this works. I want you to think of the classic example of spinning a bucket of water in a vertical circle. You may have done this before, or maybe you've just like spun a ball on a string around in a vertical circle, and it should make sense that there is a minimum speed required for a bucket of water or a ball on a string to go around in a vertical circle, or anything on a string to go around in a vertical circle. There is a minimum speed. Let's see what this works out to be. Clearly, the most critical point in the vertical circle is at the very top. At the very top, you've got gravity that's pushing on the water inside, and there's also, let's say, for example, there is some of a bucket force pushing on the water as well. So at the very top, we got two forces acting on the water. There's the bottom of the bucket, let's call that the bucket force, force B, and that's pushing down on the water. And then gravity is also pushing down on the water. Now, needless to say, there is a bunch of forces from the sides of the bucket, maybe an infinite number of forces from the sides of the bucket pushing on the water, but we can imagine those all cancel each other out for the most part. So let's call down positive, and then the equation that represents the water at the top of the path, the most critical point is sum of the forces equals MA. Bucket force down plus mg down equals MA. Now, at the exact minimum speed for spinning, the contact with the bucket becomes zero. That's where the water just starts to fall out of the bucket. So then we go back to this equation, B plus mg equals MA. B goes to zero, and we're left with mg equals MA, and we come up with a result that turns out to be pretty common. Since mg equals ma, and we also know that a is a centripetal acceleration because it's going in a circle, then we can do a substitution for a, v squared over r. We know it's centripetal acceleration. mg equals ma, mg equals mv squared over r, and we solve that. Look at that. First of all, the m's cancel out. The mass of the water doesn't matter. It could be a bucket full of bricks for that matter, but the speed is going to be the same. It'd be harder to spin them, but the minimum speed is the same, whether it's cotton or water or bricks. Solving that for the minimum speed, g is equal to v squared over r, or the minimum speed v equals the square root of r times g, which is fantastic. And this does come up pretty commonly. For example, again, the mass does not matter. This is also the same problem if you're looking at going through a circular loop in a roller coaster. The minimum speed to make the loop is equal to the square root of r times g. So of course, roller coasters are designed with this sort of thing in mind. They obviously are going to hit that curve with a speed that is greater than the minimum speed because there's friction, etc. But it doesn't want to be, you can engineer this for maximum thrills, obviously. Okay, friends, so the last thing that we're going to talk about in this video is a very special type of force called the force of universal gravitation. The force of universal gravitation is probably the greatest accomplishment of Isaac Newton's. And let's talk about what it is and how it works. So Newton thought about gravity somewhat differently than most people of his day did. He thought of gravity in orbits in a very particular mathematical way, and it was related to the law of action and reaction. He first published it in the same giant, amazing work of genius where the laws of motion first appeared, and that it was his Principia Mathematica in 1687. So before Newton, Kepler's laws were somewhat understood, and they were published a few decades earlier. And Kepler's laws talked about planets moving in elliptical orbits, and there are a couple of other things that are important as well. Kepler's laws weren't necessarily accepted by everybody, but Newton realized that in fact these laws were some manifestation of a bigger idea. And in fact, he said that not only do planets have gravity associated with them, but everything does. Everything does. That can be something small like me and you, or it can be something like planets and stars. So here's how Newton wrote it. He said, a corpuscle, meaning a body, placed without or outside a spherical surface is attracted toward the center of the sphere with a force inversely proportional to the square of its distance from that center. Well, that works way better in mathematical terms. So the force of gravity, if you put this in algebraic terms, is equal to some new constant, big G, times the product of the two masses attracting each other divided by their distance squared. That is Newton's law of universal gravitation. Or here it is, again, if you prefer, instead of using a D, using an R to represent it's the radial distance or center to center between M1 and M2. Now, this big G is actually a tiny number, 6.67 times 10 to the minus 11. So that what it should suggest to you is that you have to have really big masses to have significant gravitational forces, like we're talking like planet and star size objects for gravity to be significant. Okay, gravity is an inverse square law. What this means is if you double the distance between two bodies, their force becomes 1/4 what it originally was. Or if you triple it, the force becomes 1/9 the original amount. And we could be talking about the force of gravity just as simple as weight. After all, weight is our normal local force of gravity. So think of this. F equals ma. We now know, thanks to Newton, that F is g m1 m2 over d squared, and that is generally the distance from the center or the radius of the planet. So F equals ma, that force of gravity is going to be equal to m times a, or in this case, mg. So we set, we set g m1 m2 over d squared equal to mg, and that's the mass of u. And we find a wonderful thing that the local gravity on a planet only depends on the mass of the planet and the radius of the planet. It's given by this expression, big G, this constant of proportionality, times the mass of your planet divided by the radius of the planet squared. If we did that for Earth, the mass of the Earth is around 6 times 10 to the 24 kilograms. Radius is 6.4 times 10 to the 6 meters. We end up with, plugging the numbers in, 9.77 meters per second squared. That additional 0.03 meters per second squared comes from the Earth's rotation. So as you move further and further away from the Earth, the inverse square law tells us that the force of gravity becomes smaller and smaller as 1 over the distance squared. So there's a bunch of other things that we can actually say about this. Let me show you one of the rather interesting results. So I'm going to talk about how do we actually use universal gravitation in practice. We do have this new expression for it, and let's see that how we actually use it in calculations when we're not just talking about the local G on a planet. So we're going to try this out for the moon. So let's look at the Earth and moon. Here they are depicted as a couple of spheres, a couple of balls. That distance is not to scale, actually. There, that's about the right size comparison, but they should be separated by about 110 moons, as they are in this picture, actually taken a couple of years ago. Okay, so the calculation. F is ma. That's force of gravity between the Earth and the moon is equal to the moon's mass times the acceleration, the centripetal acceleration of the moon. Force of gravity is g, mass of the Earth, mass of the moon divided by r squared, and r is the distance between center to center between Earth and moon, and that equals mass of the moon times v squared of the moon. We're going to solve for the speed of the moon around the Earth. So I plugged in for a acceleration of the moon, the centripetal acceleration is v squared over r. And lo and behold, the mass of the moon cancels out. In other words, it could be anything in orbit. It doesn't just have to be the moon. We could plug in some numbers here. We know that g, our new constant, is 6.67 times 10 to the minus 11th. Mass of the Earth and distance of the moon are given. Plugging them in, we end up with the speed of the moon is about 1,000 meters a second or 1 kilometer per second. That's about 0.63 miles per second. Furthermore, if you're interested in bodies orbiting the sun, you would use the mass of the sun and the distance to the sun. But wait, there's more. So the orbital period of the moon, since we know that the moon's orbit, even though it's elliptical, it's close enough to be to a circle to make an approximation. The speed is equal to distance over time. That's 2 pi r over the period, where period is 2 pi r over the velocity. And plugging in our numbers, we end up with a period of about 2.3 million seconds, and that is about 27.3 days. All right, friends, See you soon. See you on the moon.